Welcome to the 7th lecture from chapter 8. We are studying VLSI design and today we will study chain delays. Chain delay, the term chain refers to the situation where we have a number of gates connected back to back. For example, the output of one gate becomes the input of another gate and so on. And we have some finite number of gates in the chain. The total delay of the chain is the sum of the delay caused by individual gates. For example, if we have 3 gates, this capital M is replaced with 3 and this is written as T1 plus T2 plus T3. The delay caused by gate number 1, by gate number 2 and by gate number 3 are added together. Here we have an example where we have a NOT driving a NAND2 and the NAND2 is driving a NOR2 and NOR2 is finally driving some load capacitance CL, right? So this NOT is a standard NOT with M is equal to 1. For this NOT, we have already derived expressions for rise and fall time delay. The input signal in this situation is a rising signal to this NOT. Since this is a NOT, it inverts the input, the output would be going down. If we have a NAND2 whose one input is connected permanently to a logic 1, it also works as an inverter. The output goes up. If we have a NOR2 whose one input is permanently connected to logic 0, it also works as an inverter. So the output should be going down. So let's see how many delays are there. This delay plus this delay. So the delay at the output of this NOT is the fall time delay. The expression for fall time delay of a NOT, the standard NOT with M is equal to 1, we have already studied that. It's TF0 plus alpha n times CL. Since this gate is with M is equal to 2, the gate capacitance would be multiplied by 2 because the aspect ratios are 2 times compared to the aspect ratio of transistors we have used here. This means this CL is 2 times the minimum input capacitance, whereas the minimum input capacitance is the input capacitance of this NOT. So this NAND gate would have a capacitance, input capacitance, the gate capacitance that is twice compared to the input capacitance of this NOT because the size of transistors are double, the aspect ratios are double, and the gate capacitance, the input capacitance is directly proportional to the aspect ratio. So it's 2 times C minimum. Right. For at this point, we'll talk about the rise time delay because the signal is rising. So TR of this NAND2 gate, this is TR, this is TF. Why TF? Because the signal was falling here. Here the signal is rising, therefore we are talking about TR. We have already studied the expression that for any M, this is 3 by 2 TR0 as long as it is NAND2, 3 by 2 TR0 plus alpha P over M times CL. So here M is equal to 2, so we replace it with a 2. 3C minimum. Why 3C minimum? Because this NOR is with scaling factor 3. This means the size of each transistor is 3 times compared to the size of each transistor here. So of course the gate capacitance would be 3 times the minimum gate capacitance C minimum. Here we have a fall time delay, NOR2, because signal is falling down. For M is equal to 3, we have already studied that the expression for fall time delay is this plus alpha n divided by M. So M is 3, so we replace it with 3. Why 4C minimum? Because it is CL in general expression and CL is given to be 4C minimum. So this is how we have it, T1, T2 and T3, and now it is time to add these 3 together to find the chain delay. So the chain delay TD, total chain delay is this delay TF0 plus alpha n times 2C minimum plus 3 by 2 TR0 plus alpha p by 2 times 3C minimum plus 3 by 2 TF0 plus alpha n by 3 times 4C minimum. And we solve it by combining like terms together, and we reach to a point where this TD can be written as this TF0 plus this TF0 is 3 by 2 plus 1 5 by 2 TF0 plus this is TR0, this is 3 by 2 TRO or TR0 plus 2 times alpha n plus this is 4 by 3, this is 3 by 2, this is 10 by 3 alpha t times C minimum. So this is the general expression for the linear equation that we can use to plot this delay dt versus C minimum. The y-intercept would be this quantity 5 by 2 df0 plus 3 by 2 dr0, and this will be a linear equation. If we have a symmetric knot and all gates are symmetric, this means if the gates are symmetric, this means the gate capacitance Cg, the input capacitance Cg is C oxide W P times L plus C oxide W N times L. This is a general expression for gate delay. C oxide times WP for PMOS, and this is for NMOS. This is the gate capacitance, input capacitance offered by the input PMOS, the PMOS transistor at its input, and this is offered by the NMOS transistor at its input. What if it is symmetric? For a symmetric knot, WP is R times WN, only if the gate is symmetric. So if you put R times Wn here, the new value of Cg, the input capacitance, the standard input capacitance, C minimum, Cg, this is the new C minimum in case the gates are symmetric, C oxide R times WNL plus C oxide WNL times L. This is C oxide Wn times L, this is R. So this is Cg, which is C minimum nu in case it is symmetric, the gate is symmetric, is R times, and this is C minimum. So C minimum for a symmetric gate is R times the C minimum otherwise. We'll keep on talking about these delays in chapter number 8 in our upcoming lectures. Thank you.